Today we're going to be discussing how to implement infinite impulse response or IIR filters in GNU Radio Companion. If you've watched any of my previous videos on digital filtering, I tend to go somewhat deep on theory. This is not going to be one of those videos. Frankly, my understanding of IIR filters is modest at best. I don't use IIR filters. I work with RF or wireless signals. You don't tend to use IIR filters for these types of signals. Why? The reason, or so I'm told, is that IIR filters don't have a linear phase response. I've learned from people that do use such filters that they're very popular for audio processing, which is much less sensitive to phase changes, and for system controls, which require a lower filter delay. Regardless, I don't use such filters. Instead, I'm going to demonstrate how to implement them in GNU Radio Companion. Let's get into it. If you look at a block diagram of the filters I've discussed in previous videos, namely the FIR filters, it would look like this. Such a filter only has feed-forward taps represented by these triangles here. An IIR filter, on the other hand, has feedback taps. That's represented here by these triangles here over on the right. So again, these are feed-forward taps, these are feedback taps. It's due to this feedback that the filter gets its name infinite impulse response. This comes from the concept that a signal input into such a filter could, theoretically, ring forever even if the signal is removed. Mind you, in an actual system with a properly designed IIR filter, the signal will eventually become so small as to be negligible. But the name is stuck. There tends to be some confusion when calculating the tap values. The calculations don't use the term feed forward and feedback. They use A and B as shown in this impulse response equation here. The A values correspond to the feedback, and the B values correspond to feed forward. Another point. IIR filters typically use the number of A taps as the defining feature. So if I come back to here, each one of the A values corresponds to a pole. When you're talking about IIR filters, you'll typically see something along the lines of a 4-pole filter. That just means that it has 4 feedback or A taps. GNU Radio Companion only provides 2 blocks directly related to IIR filters. These are the single-pole IIR filter and the one just called the IIR filter. Both implement an IIR filter. We'll start with the single-pole IIR filter first. It has a single parameter, the alpha value. This is a value between 0 and 1. This value controls how quickly an impulse will die away, with a lower alpha value corresponding to a longer time before it dies away. If I look at this particular flow graph, running it, this is the impulse response here on the top. I have an alpha value of 0.9. And then you also notice that down here on the frequency response that it's not much attenuation as you go up in frequency. If, however, I change this over to an alpha value of 0.1, notice that, yes, I start with a lower amplitude in my impulse response, but it dies away much more gradually. Also, I get more attenuation in the stop band. In case you're curious, this is what a block diagram of that single-pole IIR filter would look like. The alpha value affects 2 taps. One, it's the feed-forward tap here, and then 1 feedback tap here. And as the alpha value goes from 0 to 1, 1 being the top value, if it was 1, then you would just basically have no effect at all. Whereas if it was 0, then it would be effectively, nothing would get through. Hence the reason that you need to have something greater than 0 but less than 1 in order for this to have any effect whatsoever. Which leads us to the other block that GNU Radio provides, the appropriately named IIR filter block. The IIR filter block allows you to create your own IIR filter. This block does nothing more than implement whatever filter tab values you wish. If you look at the properties, there are 2 entries listed. These are the feed-forward taps and the feedback taps. Again, just remember that the feed-forward are the B taps and the feedback are the A taps. This is going to be important later on when you're actually trying to do the calculations, either through other programs or doing it yourself. For example, you can use it to create the single-pole IIR filter by using these particular values. But a more useful filter requires more taps. That in turn requires more complicated calculations. Those are calculations that I'm not even close to being able to properly describe. Instead, I'm going to turn to two SciPy statements. These are the IIR design statement and the IIR filter statement. The big difference between these two statements is that IIR design will calculate the number of poles for you, while IIR filter requires you to tell it how many poles it should use. Between these two, IIR design is closer to what GNU Radio's IIR filter blocks do. All of GNU Radio's built-in blocks calculate the number of taps for you, and then they actually calculate the taps afterwards. Let's start with the IIR design statement. I'm going to make a filter for the audio portion of this basic FM receiver that I've created. If you've not done so, I recommend looking at my video on creating a basic FM receiver. This follows the same steps. What you're looking at, I'm starting with an RTL SDR source, going through a low-pass filter based on the FFT. Quadrature DMOD is my frequency demodulator, and then the output, I'm coming into a frequency sync. This particular flow graph will give me this basic baseband signal here, in which I have the left plus right going from 0 to 15 kilohertz, pilot tone at 19 kilohertz, stereo signal centered at 38 kilohertz, and then you can see a little bit of the RDS signal at 57. What I want to do is create an IIR filter using the IIR design statement that will allow me to filter out the 0 to 15 kilohertz, the left plus the right channel here, and then be able to have the stop band start before we get to that 19 kilohertz pilot tone. Therefore, my filter specifications are passband from 0 to 15 kilohertz, stop band at 19 kilohertz. Let's say that I want to have a minimum attenuation similar to what I would get with a FIR filter using windowed sync and a Hamming window, which is a 53 dB. And then there's another aspect to these filters that you don't typically deal with when you're dealing with the windowed sync FIR filters, and that is the amount of ripple for certain types of IIR filters. There's different methods that you can use to create IIR filters. The four most common ones that you will see are Butterworth, two types of Chebyshev, the Chebyshev 1 and the Chebyshev 2, and then elliptical. I'm going to use the elliptical. That has ripple in both the passband and the stop band. It's also considered to have the steepest drop-off between the passband and the stop band because it allows for the ripple to be equally distributed amongst the passband and the stop band. Therefore, I need to specify how much ripple do I think I can sustain without really affecting the signal. Well, I'm dealing with audio, so I can actually sustain quite a bit, but I'm going to keep it, try to keep it relatively low, and therefore I'm going to say that my ripple is going to be half a dB. To implement this inside of here, first thing I'm going to do is I'm going to add in the IIR filter block, which, as I showed before, has two inputs. Those are the feed-forward taps, those are your B taps, and the feedback taps, which are your A taps. There's another aspect to this that if you're going to implement this in GNU Radio, you want to be very careful of, and that is the old style of taps. The way that I'm going to be implementing this filter, there is an aspect of sometimes you need to flip the sign on the feedback taps, the A taps. I don't need to worry about that, so I'm going to flip this to false. If I don't do that, the filter does not work and it just gets all kinds of screwed up. That's the first thing I want to do so I don't forget it. So now I need a way to get my feed forward and my feedback taps. The first thing I need to do is I need to add in the import block. Reason being is that the import block is going to allow me to get access to the SciPy signal library. Opening this up, I'm going to say that my import statement will be import SciPy .signal. I could leave it just as this, but that would mean I would need to actually enter SciPy.signal every time I wanted to use one of these particular statements. I'm going to make it a little bit easier. I'm going to put in an alias. Therefore, I'm going to say import SciPy.signal as sig. Therefore, now all I need to do is just put in sig dot whatever, and I'm good to go. Next part, I need to actually have the IIR design. For that, I'm going to bring in a variable. For my variable, I'm just going to call it IIR underscore taps. And then for my actual statement, sig dot IIR design, and then open parentheses. And this is where it gets fun because you have to remember what the specific order is. The very first thing I want to put in is I need to put in the passband edge frequency. I said that was 15 kilohertz. So I'm going to put in 15 kilohertz. The next part is if you're used to dealing with the FIR filters in GNU Radio, you typically put in a transition width. You're not going to put a transition width. You're going to put in the stop band edge frequency. In this particular case, this is 19 kilohertz. Next thing is it wants to know, because I'm going to be using an elliptical filter, elliptical method for designing this IIR filter that has ripple. How much ripple am I willing to deal with? So I'm going to say half a dB. Next part is what is the minimum attenuation I want in the stop band? And I said before I want this equivalent to a Hamming window, which is 53 dB. I said that I'm going to be using an elliptical filter. So the next thing I put in is I say f-type equals single quote, and then I'm just say elip. Next is it has several different ways that you can output the taps. The two that I've dealt with a little bit are what they call BA, meaning it just gives you two arrays of the B and A taps. And then there's also an SOS, which means second order section, meaning it's going to actually output a series of different arrays which allow you to put in to IIR second order sections. So basically think of it as a bunch of consecutive IIR filters, each doing essentially a second order filter, a two-pole filter. I'm going to be just doing straight BA to make things simple. So I'm going to say output equals BA. And then the last part is, what is the sample rate? I'm going to say FS equals, in this particular case, I have started at 2.4 megahertz, but once I go through this FFT low pass filter, I decimate by a factor of 10. That means that my sample rate is going to be 240E3. I could have also said samp underscore rate slash 10, but I'm just going to make it straightforward here. That's my whole thing. sig.IIR design, open parentheses, passband edge frequency of 15 kilohertz, comma, stop band edge frequency of 19 kilohertz, comma, maximum ripple I'm willing to deal with, half a dB, comma, attenuation 53 dB, comma, and then the type that I'm using to create this filter, which in this case is elliptical, which you just say elip. You could also say elliptical if you wanted to completely spell it out, but I just say elip, comma, and then the output is BA, meaning it's going to give me two arrays, one for the B, one for the A. The last part is the sample rate. And then I just said literally the sample rate is 240 kilohertz. Click apply, click OK, and now I'm ready to actually put them in here. In this particular case, I'm going to come down here and I'm going to say IIR taps. The first set of taps, actually before I do this, let me cancel that, come back to here. If you look down here at the bottom, you can see here is the taps that have been calculated by the IIR design statement. It is two arrays. Think of this as a structure. Structure means that it contains different types of values. In this particular case, it contains two arrays. I have an array here at the first part and then another array down here at the second part. This first part, that's for the B taps. The second part is for the A taps. Now remember, B means the feed forward, A means the feed back. To put that in here, I'm going to say IIR underscore taps, and because they're zero indexed, the first one will just say 0. So open brackets, 0, close brackets. Second one, IIR underscore taps, 1. Again, this refers to the first part of the array, this part right here. The second one refers to the second array down here. And I can even put my cursor over it to see what values it's pulling. And I can see that, yes, that matches these values down here. And do the same thing for the second one. If I click apply, notice that it's saying the exact same values as these ones down here. I've now created my filter, and I can actually see that. I'm going to move this frequency sink to the output here. Let me get my sample rate correct. It's a half. Look at my output. And notice that, yeah, I can still see the other things, but they're significantly reduced. Therefore, they're negligible compared to my left plus right audio here at the beginning. All I would need to do now is add in the rest of the different components that I need in order to actually get an audio output, which I can go ahead and do that real quick. The one thing I'm not going to do though is I need to decimate downsample this. This is 240 kilohertz. No audio card will handle that. I would typically go down to 48. I don't want to use a rational resampler because the rational resampler has its own built-in filtering. I don't want to mess it up that way. Instead, what I'm going to do is I'm going to kind of go old school, and I'm going to use a Stream Demux to do the downsampling. I'm literally going to throw away samples, and in this particular case, I'm going to say a null sync for the samples that I'm going to throw away. And I'm starting 240 kilohertz. I want to go to 48 kilohertz. That's a factor of 5, which means I'm going to keep 1, and I'm going to throw away 4. The rest of this, I can go ahead and add in a audio sync. Say 48 kilohertz. And let's see what that does.
To $1,500 in prepaid cards when you add 2 lines of mobile to a qualifying gig bundle. Don't wait. Call today.
That works. That's with the IIR design statement. Last thing I'm going to cover is the IIR filter statement. I'm going to keep this particular flow graph here. I'm going to keep everything the same. The only thing that I'm going to change is up here in my IIR taps variable. I'm going to open it up, and I'm going to change IIR design into IIR filter. The difference between IIR design and IIR filter is that in IIR filter, you have to provide the number of taps. It doesn't calculate it for you. The taps that I calculated for the IIR design turned out to be a 7-pole. So I'm going to start by saying, okay, that's a 7-pole. The next thing that it wants is the passband edge frequency. I've already got that. It does not need the passband or the stopband edge frequency. I'm going to keep the same ripple, the same minimum attenuation. Another thing that IIR filter needs that's different from IIR design is it needs to know what type of filter, meaning is this a low pass, a band pass, band reject, whatever. For that, I'm going to enter in called B-type. B-type equals low pass, again surrounded by single quotes. Everything else I should be able to keep the same. Click on apply, and what I wind up with is, well, golly gee, I wind up with pretty much exactly the same statement as variable taps that I had before. And what you're going to be seeing here is when I'm running this particular flow graph, it's going to be the same as the previous one. The only difference is that because I probably blew out some speakers when I played the radio the last time, I put in the Quadrature demod. I did a /2 in order to keep the volume from blowing anybody else's eardrums out. And apologies for that if I did. When you play this, it should look very similar. It does. Notice that I've got still the left plus the right here. It's just lower on the amplitude because, again, that's /2. And there you are. Those are the 2 basic statements that you use. I'll put links in my description to give you to tell you where you can find the web pages outlining how to use those particular variables if you want to add different types, if you want to create bandpass filters and so on. But again, this is about as far as I'm willing to go when talking about IIR filters because, again, my knowledge is just not up to snuff if I really want to dive into the theory. Therefore, I'm going to leave it here. Thank you for watching, again, this video, and I will see you next time.